Mathematics and Height Maps by Sam Hartzai. Where to begin? Well, about 5 months ago, I started making a video game, and I wanted to use that video game as the topic of my final project. But while researching for this project, I realized that using the entire video game as my topic would be simply too broad, so I had to focus in. I decided to go with a somewhat small but important part of game development and mathematics, that being height maps and matrices. I've used height maps for many different aspects of my game, and height maps are used for far more than just video games. A height map is usually made of a rectangular grid of pixels, also known as a raster image, but the computer sees it as a matrix. What is a matrix? Well, similarly to a height map, and the reason we are talking about them, matrices are also grids. A matrix is a rectangular grid of numbers or mathematical expressions that are used to represent a mathematical object, like in our case, a height map. What is a height map? A height map is used to record the elevation of a surface at different grid points across the surface. The elevation data is converted to a value between 0 and 1 to simplify things and determine the visual color that you will see in the image. A normal image uses 3 color channels, red, green, and blue. Each color channel has 8 bits associated with it to give it a color. The values are mixed together to get each color outside of red, green, and blue from a total of 3, having 24 bits. In a height map, however, because there's only one type of data being stored, we only need to use one color. For this we use shades of gray, 16.7 million shades to be exact. Through this we can get high-resolution images with millimeter-level precision. After each pixel is recorded, the data from each pixel that makes up the grid or image is stored into a matrix. Here's our real-world example. Here we see a landscape. This is really just a 1x1 grid. Trying to make a height map out of this resolution doesn't really work because you only get one height value. So unless you only need the direct center of your landscape as a height map, you should try to increase the resolution as much as you can. There's also a profile view of the larger diagram for reference. Increasing the resolution to 3, we see that we are able to pull a lot more detail out of the surface. Again, I include a profile view to show you what it looks like from the side. This is a good start, but we don't really have anything to measure. Adding a curve to the surface allows us to see the height map in action. The raycasts in the center of the curve are shorter than the raycasts on the sides of the curve. This means that the matrix of pixels, you will see larger values in place at the center of the curve. An example of this might look something like this: 0.5 on the left, 0.7 in the center, and 0.5 on the right. This is a good place to start to see detail, but we won't be able to get all the detail until we crank up the resolution. Here we see, when we add more variation to the surface and increase the resolution to 6, we increase the number of rays cast from 9 to 36, and thus the resolution is quadrupled in our final height map. Here you can really see the potential in height maps. How does this apply to matrices? Well, let's take this example. We have a matrix labeled with columns x1, x2, and x3, and the rows as y1, y2, and y3. We also see a 4x4 grid on the right. This represents our landscape. The values stored at each pixel in the image and in the landscape can be applied to the corresponding space in the matrix. Here you see A has the index x1, y1, and thus gets the x1, y1 value from the grid, being 0.7. Next, B will get x2, y1, or 0.8, and so on. Once you have the entire matrix filled with your height map values, you are done. Here's that resulting matrix. And here are a few more examples of some matrix calls. The beauty of matrices for height maps is that you can be as precise as you want for the landscape you want to make. And the uses of height maps are endless. I use them to model landscapes in my projects, I use them to place objects in those landscapes, and I use them to record the position of the player for pathfinding AI. Matrices and height maps are used all over the place though, not just games. 3D scanners use light rays to get the distance from an object from lots of different points to reassemble it in a 3D modeling software, like a 3D height map. Anytime you look at Google Earth, you are seeing height maps made from boats mapping the ocean floors and satellites mapping hard-to-reach terrain on the Earth's surface. Height maps are used by architects, designers, engineers, and basically anything else. Matrices find their places in data science, business, engineering, and design, just to name a few, and you couldn't have a height map without a matrix. Now here's a short animation I made to demonstrate the process a computer uses to make a height map. Imagine you just finished sculpting this beautiful mountainous landscape, and you're trying to figure out how your computer knows where all of these faces are, where every point is on the map. Now, to do this, we're going to have to focus in on a much smaller part of the map. We can add some deformation to the face, and then we'll use a plane and some arrows to act as our camera and our raycasts. Here you can see that we have 5 rows of 5 raycasts, giving us a resolution of 5. Now each raycast has a height value associated with it, a distance from the camera to the terrain. This distance is normalized and divided by the length of the vector to give us a height map value between 0 and 1. With this, we can do whatever we want, like place a duck there. Heck, we could cover the whole world with ducks. Thank you for watching.